Hi, today we will show you how to solve a conversion diversion nozzle using ANSYS. First, we are opening ANSYS. The first step is to draw the geometry. We select geometry, then we select a line, make it 2D, and then we start drawing the nozzle. Then we go to concept and select surface from sketch and select any line, apply and generate. Then close it and go to mesh, double click on mesh. Then right click on mesh, insert, then face, apply. Then we rename the inlet and outlet and the wall. Then we do sizing for the inlet outlet. And we do sizing for the wall too. Then we refine. We faced an error, so we have to repeat the sizing and refinement. We will repeat it now. Insert sizing, the same steps for sizing. Okay, and now this is the mesh, and we
Okay, so now we just update the mesh. so that we can use it for the setup and the solution and the results. Just waiting for it to load. Updating the mesh. So now we do the setup. We choose the options as double precision and the processing options as serial. And we start. So now we have our platform for our setup. Firstly, we choose density based for the type when we deal with the general. And as for the models, our energy is, we have an energy equation and the viscous should be inviscid. There should be an inviscid fluid. So now we go for the materials and our density should be ideal gas. It shouldn't be constant since we're dealing with ideal gas in this case. We change it, we close it, and then we go for our reference mesh. We compute it from the inlet, as everything is done from the inlet. And then we go for the most important part, which is the boundary conditions. At the inlet, we have pressure inlet, not velocity. Pressure inlet, a gauge total pressure of 110,000 Pascal, and a supersonic pressure of 100,000 Pascal. After that, we go for the outlet of the nozzle, whose pressure will be 4,000 Pascal, according to the question. And we put the operating pressure as 0. Just checking, and then we go for our solution initialization. Put a standard initialization and we compute it from the inlet. We initialize it and we run the calculation to see, we put it until we see when our value will converge. When it converges, we know that our mesh will be right. And we put a number of iterations of around 2,000 iterations. And we keep the iterations going until the value converges. Till the x velocity, y velocity, energy, and continuity converge. We have a converging value at iteration number 1324, which means our mesh will be correct, is correct. They don't diverge. And after that, we have finished the geometry setup, mesh, and solution, and right now we go for the results of our converging diverging nozzle. Now we go for the results. And we want to see how the pressure, velocity, and temperature change as you go through the nozzle. We go for a contour plot throughout the nozzle. And we can notice sharp corners, which will cause a spike increase or decrease in our values. But first, we're going to plot the pressure as it goes through the nozzle. We put an actual symmetry, and we vary the pressure as it goes through the nozzle. We put around 110 contours, and we apply it. And we can see that the pressure is high in the inlet, and it decreases as you go through. and it decreases the outlet. You can notice a sudden change in pressure at the corners. We can improve this by adding fillets or making curved corners instead of making sharp corners. And now we put a line so we can, throughout the nozzle, so we can check, so we can get an actual graph of the variables against the length of the nozzle. And we go for a chart. And for our data series, we'll put it as the line. It is a function of the length. And the x-axis will be the x, which is the length of the nozzle, and the y-axis is our variable which we want to vary through, which varies as a function of the length of the nozzle. So in this case, we want to vary pressure as a function of x. Just change the series to line 1. Okay, show us line 1. Now for our y variable, we want to vary pressure. We apply it and we find out that the pressure is high at the inlet and decreases rapidly at the corner and decreases to less than 20,000 pascal at the outlet. We do the same thing for velocity, increases throughout as you go from inlet to outlet. Again, spike increase because of the sharp corners. And the temperature decreases as you go to the nozzle. Again, a sudden decrease because of the sharp corner. Goes to a value of almost 140 Kelvin. And that's about it for our tutorial. Thank you.